Welcome to Technical, a bi-coastal podcast where Silicon Alley meets Silicon Valley. This is a podcast for technology professionals, so we go pretty deep, and in this case, all the way to a subatomic level. I'm your host, Bill Kozel of TechWriters NYC. At TechWriters NYC, we translate geek speak. Visit us at techwriters.nyc. My guest this week is Bob Sutor, Vice President of IBM Q Strategy and Ecosystem for IBM Research. As with my very first guest, John Wallachy of IBM Watson IoT, Bob is an IBM lifer. He began his career there in 1984 and has held a number of positions, culminating in his current role as IBM Q Program Leadership for Quantum Computing Education. Bob has an AB in Mathematics from Harvard and an MA and PhD in Mathematics from Princeton. I'm delighted to have him on my program. Welcome to Technical, Bob.
Thank you very much.
Now, this is a program for technology professionals, but it's not a program for physicists. Without dumbing down things too much, can you break down the basics of quantum computing and your IBM Q systems?
Sure, and that's good because I'm not a physicist either. I'm only a mathematician.
Yes.
And you know, that distinction, I believe, is real. Quantum computing is based on quantum mechanics, which is one of the strangest parts of science, and it's parts of physics. Mm-hmm. And it wasn't really until a couple of years ago that I started looking at it. And I in fact, was very pleased to find that there are mathematical computer sciences approaches to this. Basic idea with quantum computing goes back to an observation by Richard Feynman in 1981, is that if you think of classical computers, and by that, you know, it's the chip that's in your smartphone, that's in your laptop, or the servers that drive the internet today. If you look at that type of computing, the basic architecture, which goes back to the late 1940s, they asked, are there some types of problems where these computers will never be really effective? That is, we have found that they're really useful. And in fact, in the last 10 years with the whole smartphone revolution and the millions and millions of apps, obviously, there's a lot of use to them. But are there gaps, right? The nature of some of the things we would love to compute such that these classical computers just won't work. And the reasons typically why they wouldn't work is once you start working on the problem, running the code, they blow up in one of two ways. They either blow up because to actually complete the computation, it might take tens or hundreds or thousands of years, or they blow up because of memory, that there's so much information that would need to be stored that you just can't possibly fit that into a classical computer. What sorts of problems are those? Well, Feynman's observation was that it's problems that relate to nature. And by nature, here, we'll use that as a proxy for saying molecules, atoms, molecules. And this can be anything from the simplest, most molecules all the way up to the things we use in healthcare, the lattice type molecules we use in material science and things like that. And he was absolutely right. In fact, when you try to represent the information for a lot of these molecules, the amount of space just grows exponentially. I mean, it gets huge really fast. And you don't have a hope with classical computers. But this is where quantum computers come in. Quantum computers are built on the same principles of quantum mechanics. There are two of them. One's called superposition, the other called entanglement. And if you build a computing model built on those ideas, the general idea is that, well, since nature operates according to these principles, if you have a computer that operates on those principles, you might be able to map one to the other much more easily. And so that's why a lot of the early applications are around chemistry. But people are also looking for applications in general optimization, in artificial intelligence to augment the mathematics, the computations down deep in there, possibly in finance. So a few other areas. Quantum computers will not replace classical computers. They will be used in a complementary way, we hope, for tackling certain types of problems.
Yeah, and you recently announced a hybrid model called Qiskit and Qiskit Aqua that blends quantum computing with classical computing. Can you tell us about that?
Sure. So first, Qiskit, just to fix the name, it's Quantum Information Science Kit. It's a software development kit that people use to write software that runs on IBM's quantum computers, the IBM Q machines. It works with Python, a very common programming language. But the question is, well, do I have to rewrite everything myself, right? It's a brand new type of system. I want to do something. Do I have to write even the most basic things over and over again? And the way people have solved this using classical programming languages is you build libraries. And the libraries are reusable code that you can pull in and say, okay, someone's already written a great algorithm to do this. I'll just reuse it. So first, Qiskit Aqua does that. It does it for several areas, for chemistry, artificial intelligence, and for optimization. So that is, it provides some standard quantum algorithms in library form for people to use. But what I think is really more important is how it tackles this problem of how do you mix what you can do with quantum computers now, what we can increasingly do, with what maybe you already figured out how to do classically. So again, on classical computers, there are existing applications that work very well in a wide range of areas. And this is where we talk about domain experts, people who focus, let's say, on chemistry or financial services types of calculations. What if you already have those applications and they do most of what you want, but you'd like to do a little extra with quantum? So what Qiskit Aqua does is it makes it very easy to interface these together. So people don't have to learn brand new languages. They can work in the applications that they know, that they're used to, that they have great value for. But increasingly, they can interface with IBM Q and do some types of calculations where quantum computing can now do a better job. It's very open-ended, it's extendable, it's modular, and it's open source. So we hope what we announced last week is really just the beginning of a broad collection of libraries that many people will find useful.
You say it uses Python. How does that work with quantum computing?
Well, what a lot of people don't realize actually is with quantum computing is you're not only working with a quantum computer. Most of the setup to use a quantum computer is just done classically. So you would write some Python code, typically. You would pull in the libraries. You would import the libraries for Qiskit. Those libraries have methods or functions that allow you to connect to either IBM Q hardware or quantum simulators. And then using this higher level language, you can construct your application and away you go. So it allows you to use the classical programming language, Python, what it is best for, while mixing in calls to the quantum computer to do what it does best. So the world today, even with the quantum computers we have right now, is already a hybrid of classical and quantum. So making these work together as seamlessly as possible is a goal of ours from the very beginning, and it continues with Qiskit Aqua.
What will the software of the future look like?
So the software of the future is going to be, more interesting, let's say right now. For one, we are going to need a new set of software developers that understand quantum computing. It is not simply taking what you know using classical computers and moving it over, and therefore continuing to keep doing what you're doing on a quantum computer. You program quantum computers in completely different ways, and it's not even using a different language. That's not the point. We have these stickers. In fact, I'm staring at one of them right now that says, "You're thinking too classically." And what that means is, those things I mentioned before about superposition and entanglement, what they lead to is a completely different set of fundamental building blocks or gates from which we build our algorithm. And unlike classical, where you can treat bits and bytes in isolation and manipulate them in a very serial sort of way, the qubits in a quantum computer work together in ways that you set up. They get entangled. And so the process from going from the beginning of the algorithm of setting up the problem to ultimately getting the answer at the end is completely different. It's not quite the step by step way that people are interested, that people know how to do right now. So we will have this new class of quantum software developers. Now, they will be working to develop libraries, as we discussed a little bit earlier. And ultimately, I think that people will be using quantum computers. Most people, most software developers, will be using quantum computers fairly transparently. That is, they'll just make a function call, they'll say, do this, and they may not know under the covers a quantum computer is actually being used. But there's a brand new stack. There's a brand new hardware stack. There's a brand new software stack. So to the degree that's already hybrid, it's going to become much more so in the future.
Now, what types of atoms are used in quantum computing?
So I'll interpret that as what sort of materials.
Okay. Yeah, I don't know. It's is it molecules, or is it atoms, or is it electrons? What is it?
So yeah, so let me describe it. So what we do is we fabricate our quantum devices right here in our labs in Yorktown Heights, New York. It's about 30 miles north of New York City. This is the T.J. Watson Research Center. It's about 1,100 scientists and staff here. And we build the actual qubit devices. They are superconducting devices. And for those people who know, they are built on the technology of Josephson junctions, or so-called transmon qubits. What this really boils down to is that they are analog devices that must operate at extremely cold temperature. And that's why they're superconducting. And so the materials that we construct them from are these special superconducting elements or atoms and molecules.
It's colder than deep space, right?
That's right. Deep space is about 2.7 degrees Kelvin. And these run at 15 millikelvin, 0.015.
How does a material withstand that temperature?
Well, most of them withstand just fine. Most of the actual chassis, or what we call the cryostat, if you've ever seen a photo of one of our quantum computers, it's the inside of it. It's been termed different things. Some people called it a steampunk chandelier. It looks like this golden, chandelier that's probably about 3 feet tall. It has different platforms. That's constructed of multiple metals. So there's steel, there's copper, there's brass, there are the superconducting alloys and things like this. A lot of that has to do with either the electronics of controlling the qubits and reading them, or the actual refrigeration. So if you just take a piece of brass, you can cool that down with no problems that cold. It just basically stays a piece of brass. The trick is, though, this is a highly engineered object. And it's made out of many metals. It's multiple platforms. They're connected together. There are superconducting coaxial cables coming down. If you see a photo, they're the things with the loops in them. If this wasn't engineered correctly, going back to your question, as it gets colder, the metals would shrink to different degrees based on the type of metal that it is. And what would happen the thing would just rip itself apart, because the metal, some of it would be going a little faster, some would be going a little slower. And you'd open it up and you'd have a pile of metal shards on the bottom. So you start by building your chips, and then you start by engineering everything else around it so that it cools down gracefully without damaging itself. By the way, in case anyone's curious, it takes about 36 hours to cool down from room temperature to that 0.015 Kelvin. So you do it slowly and you do it carefully.
China and the European Union are pouring lots of funding into quantum computing. How can the U.S. keep pace?
So there are several ways. First way is that we believe that the United States government needs to have a very healthy, supported scientific program around quantum computing. And there have been a couple of bills introduced in Congress lately that we support that would set up a national quantum institute that would fund core research into the creation of these new machines. And this is critical. While the science that underlies quantum goes back, quantum information theory to the 1960s, quantum mechanics all the way to 1900, we're in the very early days of being able to actually build quantum computers. And to get from where we are now with a relatively small number of qubits to the point where we can get ultimately millions or tens of millions of qubits are going to require a lot of research. Going to require a very large number of people, not just quantum scientists, material scientists, chemists, computational scientists, mathematicians, computer scientists, all sorts of ways. And these need to be supported somehow at every different level. When we're building quantum computers, as we're building this program, because it is so completely new, this is not version 2 of anything. This is version 1. We need to create everything right? So we need to create the entire hardware stack, the entire software stack, everything around it. We need to go in and we need to use the best materials. We talked about superconducting materials. We need to have the best amplifiers, the best filters, the best microwave form generators, things like this. So the breadth of the amount of research and engineering that has to be done to move us from these early stages through the next few decades is very broad. It's very exciting. And as I said, we support this effort in the United States to support it, to support researchers.
And who else is working on quantum computers, and how do the various technologies differ?
So most of our competitors in the IT industry that have been involved with hardware are somehow involved. And there are different approaches. As I said, the technical name, the superconducting transmon qubits. There are several companies, one or two startups that are working on this. The fundamental unit in quantum computing is something called a qubit. So a basic question is, well, how do you make a qubit? And that's the transmon supercomputing thing. Are there other ways of making qubits? Well, it turns out there are. That there are several different ways, and they all have pluses and minuses. There are some people who are banking on major discoveries to come. I find it kind of humorous because they seem to pretend that we've already discovered these things when we haven't yet. But in any case, people are actively looking for ways that will create what I'll call good qubits, very low error rates, qubits that last a long time for computation. Most of the other approaches, we believe the cons outweigh the pros. We think our technology, and again, it's technology that's also used with many variations by other people, offers the highest quality qubits where we can control the noise, that is the errors that creep in, and will also allow us to scale to the many qubits that we need. Now, all that said, if you look across the world and you look at all the labs, commercial or universities, there are so many brilliant people pushing the state of the art of this. Is just daunting. So it's going to be very exciting over the next few years as we all push this. And in fact, I say with no hesitation that I think quantum computing will be the most important computer technology for the rest of the century.
I've been reading The Last Man Who Knew Everything by David N. Schwartz. It's about Enrico Fermi. How many of Fermi's fingerprints are on quantum computing?
Well, Fermi was obviously a very influential physicist in the middle of the last century. He was seminal in being able to understand and really blend together, let me say, the more classical approaches to physics and the more modern, the more quantum-based approach. Now, he was one of many, I will say. Mm-hmm. Back then, and even a few decades before that, you would see these front page articles, letters from Einstein to Heisenberg or Schrödinger. They'd appear on the front pages of newspapers. And so you were asking about different countries and different things like this. Well, this was a matter of national pride that Einstein was right and so else was wrong. And it's kind of funny to think back now. The foundation for quantum computing through quantum mechanics, but also just other parts of physics, have been laid by many, many people. If you go back and look at the Nobel Prize winners in physics in the last century, so many of them, the big names in addition to Fermi, have had a very big part in all of this. And it's daunting to see. And by the way, all these people, they didn't actually have a quantum computer. As I said, we've only been able to build them the last 10 to 20 years. So a lot of that work was theoretical. We think of it as quantum foundations at this point, whereas the period we're in right now, we think of as the quantum ready phase. We have computers, they're small. It's time for people to jump in, start learning how to code them, start building algorithms.
And finally, there's a rumor that quantum computing will do away with things like cybersecurity and blockchain. Is that true?
Yeah, no, not at all. Not at all.
Oh.
No, this is sometimes it's funny to see headlines that get written about some of these things. So as it concerns cryptography, the root of this is back in the 1990s, a mathematician named Peter Shor developed an algorithm, which is now called Shor's algorithm, which showed that if you had a big enough quantum computer, you could factor numbers exponentially faster than any way we know how to do today. And that is, instead of taking years, it could take seconds. Now, that sounds interesting. And however, I don't think most people spend their days worrying about how to factor numbers until you point out to them that a lot of the security that we use, not all, but a lot of the security that we use, is based on our inability to factor large numbers, things like RSA. And in particular, our inability to factor products of two prime numbers that are relatively close together. It would take so long to do this if you tried to crack it. And therefore, since you can't do it, it's secure. Things like this. Well, okay, so people connect these two, quantum algorithm to factor numbers with security based on factoring, and they say that we have a problem. What they don't actually remember to say is this. Right now, for example, the biggest prototype quantum computer we have today, IBM has, is 50 qubits. We would need a quantum computer on the order of 100 million qubits to do this type of factorization. And there are technical reasons why we need that many. It has to do with creating logical qubits that are fault tolerant and so forth, things like this. So just think of that. You have 50 of something, and I tell you, you need 100 million. Are you going to lose sleep tonight over this problem? So we estimate it's going to take 15 or 20 or 30 years before this even becomes a problem. Now, moreover, there are other methods that have been created, are in the process of being standardized, what people call post-quantum cryptography, things like lattice methods, they're called, that are not amenable to being broken by quantum computing. So what people should be doing, because we know that they're paying a lot of attention to their security plans every single day, right? That's what people should be doing. People should be looking into investing in and converting to post-quantum cryptographic methods over the next decade. So again, don't lose sleep tonight. The sky is not falling. But just as everything about security, you need to understand what you've got. You need to understand the threats. You need to update to the latest software. This should simply go in the list of things you do, and there's no problem.
Anything else you wanted to discuss?
I just want to say, this could sound fairly abstract to a lot of people. These quantum computers. What are they? People can use them today. If you just do a search on the web, look for the IBM Q Experience, and you can sign up, and you can use our basic 5 and 16 qubit computers for free. For the 5 qubit machines, there is a very simple drag and drop interface that you can start programming instantly with quantum computers. The 16 qubit version, you're going to have to do a little programming in Python, but we provide all that. There are plenty of videos to get you up and running. So far, over 85,000 people have taken advantage of this invitation, and they've run over 4.5 million computations. For those people who, typically corporations or universities that want to get even more serious about this, we have the IBM Q Network, and it has various parts to the program, but this is where we will make the latest and greatest quantum computers available to our clients. And for that, they should speak to someone like me. We have been very open about our quantum computing program, IBM Q. We have made it available. We don't hide behind simple websites or photos. We let people use real quantum computers, right? We don't just have simulators. A simulator, while useful in many ways, frankly, is just classical computers. If you just have a simulator, you're not really doing quantum computing. You're simulating using it. So we let people have access to this. To date, we've had over 80 papers that have been written using the Q Experience. So we are already in the last 2 years helping to drive the research in this area, as well as prepping this next generation of software developers and people who will be developing code for quantum. Now, the people I'm especially interested in, I love all our users, but I'm really hoping a lot of college students, a lot of graduate students jump in there and start learning more about quantum computing through the Q Experience. If you think about it, if you're in college right now, we believe that there's a good possibility in the 2020s that this is where quantum computing will really start to come of age. That is, we will get to a point of quantum advantage where we can say right over here, there is a demonstrable and significant difference using quantum compared to anything we know how to do classically. The people who are in college right now will be in the workforce in the next decade. For them to become what I call quantum native is an excellent idea. And so if there are any computer science or mathematics or physics students out there or anyone else, jump in there now. We provide everything you need to get up and running.
Well, thank you, Bob.
Okay. Well, thanks for asking me. I enjoyed it.
You can learn more about IBM-Q at ibmq.com/IBMQ, and you can even play with a quantum computer at a link that I'll post on my site. That's it for this edition of Technical. Technical is a production of Tech Writers NYC. For Technical and Tech Writers NYC, I'm Bill Kozel. See you next time.